Equipped with a very basic understanding of random variables and non-commuting physical observables, such as the rotation experiment we did in the first slide, let's have a look at a very profound difference between quantum and classical logic. Now imagine that we have a classical physical system, something we have worked with before. Let's say we have a particle moving along a one-dimensional line, and we claim that we can ascribe a state to this particle in terms of its position and velocity at any given point of time. For instance, we might say that at t equal to 0, where we are beginning our experiment, the particle has position x and velocity v, and then we evolve the system in time using Newton's laws of motions. So in other words, given the initial position and velocity, we know for all future times the position and velocity of the particle. Now this is all fairly good, and this is something we have been doing all along in our studies so far. But here is a very interesting point. In claiming that my particle has position x and my particle has velocity v, we are making two assumptions. One, that the position of the particle is precisely measurable. Likewise, the velocity is precisely measurable. Even more interestingly, that it's okay for me to claim that the state of my particle is position x, and notice that I'm emphasizing the word and here, because this and is nothing different from the binary logical operation, binary logical ANDing operation that we do when we are combining logical systems. So we're saying that the particle has position x and simultaneously the particle has velocity v. This idea is profoundly challenged at the quantum realm. This ANDing of measurable quantities, this claim that the state of a particle is completely specified by quantities which we can measure, which kind of behave like labels to a particle, which we can then use to make future predictions. So let's see what happens at the quantum level by means of a simple experiment, rather the simulation of an experiment, where I'm going to show you that even this very basic idea, which we take for granted, has to be thought about a little bit more carefully. So here is our setup. Now, I have what I'll refer to as a z apparatus, and you can look at the coordinate axis that we have drawn here. So we have x, y, z, in terms of which we're going to understand this experiment. So when I'm saying that this apparatus is the z apparatus, what I mean is that its length, that the longer side of its edge is pointing along the z direction. And then I'm going to throw in a bunch of random arrows. If you were to think of this system classically, you can think of these arrows as vectors in space. Now in any experiment, we have a system that we want to study. So in this case, the system that we want to study are these arrows. And then we have a measuring apparatus. So the system and the apparatus interact with each other, and somehow the apparatus gives us a value for whatever we want to measure. Now how the interaction between the apparatus and the system is going to happen technically, we're going to ignore that for now. We're just going to see that if I throw in a bunch of randomly oriented arrows through the z apparatus, and let's say for simplicity that somehow the apparatus is measuring whether the arrow has a component along the positive z axis or a component along the negative z axis. So somehow it's measuring either a projection of the arrow along the z axis, or it's forcing the arrows to assume a projection along the z axis. Is something we're going to leave as an open question, but it's going to tell me whether the arrow has a positive z component or a negative z component. So let me quickly show you one example of what I mean. So let's say this is an arrow. It goes through the apparatus and somehow it interacts with the apparatus to give me an arrow which points up. And I'm going to take another sort of randomly oriented arrow and I'm going to let it pass through the system, and this time again it gives me a positive z orientation for the arrow. Now I'll have another arrow which looks like it's pointing along the x-axis, right? So classically, you might think twice before saying that it does indeed have a positive z component or not, but let's just pass it through this apparatus and see what happens. Well, if you pass an arrow which looks like it's pointing completely along the x-axis through this apparatus, it seems that it's still giving me a z component. So that's already a kind of a red flag for us to think a little bit more carefully about. And let's say I have another arrow, and in this case the arrow is pointing along the negative z direction, and as it passes through the apparatus, we see that it comes out completely unchanged. Now this is an example or rather a very stripped down version of an experiment which was literally performed by Stern and Gerlach. So this is a bare minimum version of what is called the Stern-Gerlach experiment. I'm going to talk a little bit more about that later, but for now, let's say we have this observation, right? We have the z apparatus, I have these randomly oriented arrows which I pass through it, and what we notice is that perhaps 50% of the arrows come out facing up like this, and the remaining 50% come out facing down like this. And just to test another example, so I have this arrow which was oriented pretty much like what one of our initial arrows was, but this time when it interacts with the apparatus, it comes out facing down. So on an average, we see that 50% of the arrows come out facing up and 50% come out facing down. Alright, that still seems something which we can explain classically. We might say that, okay, we have randomly oriented arrows and this apparatus is projecting these arrows along the z-axis, and you would guess that, okay, if it's completely random, then around 50% would come out facing up and 50% would come out facing down. So that's fair and good. And now I'm going to use my classical intuition and claim that these arrows which we have at the output can be described by a set of two values, arrow pointing up and arrow pointing down, and I can associate a classical state to each of the outputted arrows as either being z equals +1. So I'm going to refer to +1 as an arrow pointing up and z equals -1 as an arrow pointing down. And this is again continuing the notation we introduced last time when we talked about coin flipping, and we said that heads is perhaps +1 and tails is -1. So I'm going to use the same notation. And notice one thing, that if an arrow was already pointing up or down, what we observe from this experiment is that it comes out through the apparatus completely unchanged. So equipped with this state of the system, I'm going to do another experiment now. Now this time I'm going to take all of the arrows which were pointing up along the z-axis, and I'm going to pass it through an apparatus which is now oriented along the x-axis. So the way I've depicted that in this slide is that I have the longer side of this apparatus pointing along the x direction. Now let's see what happens in this particular experiment. So again, I have all arrows pointing up, and I'm going to take them one at a time and pass it through the x apparatus. Now presumably, if this were a classical system and all the arrows were already pointing up, it shouldn't have any x component, right? That's what a classical vector would do, because it doesn't have any projection along the x-axis. But let's see what happens in this case. Well, it seems that it has given me an x orientation, and this time it so happens that it's pointing along the negative x direction. I take another arrow and pass it through the x apparatus, and it turns out that this one has an orientation along the positive x-axis. I have a third arrow, and this time it again seems to have an orientation along the positive x-axis, and that's my final arrow, and this guy is turning with a negative orientation along the x-axis. So what we observe is that again 50% of the arrows come out facing right and 50% of the arrows come out facing left. Now notice my sample size is fairly small in this case, so I'm just showing 4 arrows or 5 arrows, and so if you were to literally do this experiment, you might not see 50% exactly, but the idea is that we are able to repeat this experiment with multiple or maybe thousands or tens of thousands of such arrows, and as you take more and more sample sizes, approximately 50% will come out facing right and 50% will come out facing left. Alright, we might still say that perhaps our classical intuition works, and the state of the arrow at the output of both the Z apparatus, which we passed the randomly oriented arrows through in the first slide, and now that we've passed it through an apparatus which is oriented along the x-axis, I might be able to define a state set which has a Z value of up down and an X value of left right. And maybe if I extract from this system a bunch of arrows which let's say have Z equals +1 and X equals +1, I can claim that the state of these arrows is now Z equals +1 and X equals +1, or Z up and X right. Now, in order to test this intuition, we might be able to do another experiment. I might decide that I'm going to pass this system with a Z equals +1 and X equals +1 through another Z apparatus, just to check that indeed Z turns out to be +1. So classically, that's what our intuition will tell us, right? That I have two values, the Z component, which is up, and the X component, which is right. In this case, I'm going to pick only these arrows from after having passed them through both a Z and an X apparatus, and I'm going to again pass the system through a Z apparatus, just to make sure that the Z value does turn out to be +1. So let's see what happens. Here it is. Here's one of the arrows, and I'm depicting it with a 45-degree angle, which some of you might complain about, because in the quantum case that might not be entirely correct way of depicting it, but classically that's what my intuition tells me. So I pass it through a Z apparatus, and what I observe is that I end up having an arrow pointing down. Now, where did this Z equals -1 or a down pointing arrow come from? Because at the input of this apparatus, I only had states which had Z equals +1 and X equals +1, apparently. Let's try another one. Maybe there was some error. So here's this arrow. Okay, so that's passing through the apparatus, and it's again pointing down. And we have a third one. All right, this one goes up, and then we have a fourth one, and this one also goes up. And what we observe is that even after having prepared the system with a Z equals +1 and an X equals +1, if I again try to measure my Z component, I have complete uncertainty about what direction will the arrow show up. And that's one example of the uncertainty principle at play. Now, if you reflect upon what we just saw, you might be completely surprised as to how did we get arrows pointing down when we started with the system with arrows pointing up as Z equals +1 and an arrow pointing right. You might also be tempted to think about what will happen if I now take this system and pass it through an X apparatus. Evidently, it seems that the binary logical ANDing operation, that the input state to this system had Z equals +1 and simultaneously it had X equals +1, is somehow failing us. In fact, Z followed by X apparatus, if you think about this, and maybe we'll develop this idea further in future in a future video, Z followed by an X apparatus turns out not to be the same as an X apparatus followed by a Z apparatus. This experiment that we've just shown, where having prepared a quantum state with a definite X value followed by a definite Z value, or the other way around, having prepared a quantum system or a system with a definite Z value followed by preparing it with a definite X value, completely transforms the system in a way that the last measurement, if I know that I have passed it through a Z apparatus followed by an X apparatus and then extracted the arrows with an X equals +1, for instance, has completely destroyed all information that we had about the Z value of the arrows. And this is what the uncertainty principle tells us, that at the quantum level, states of a quantum system may have values or observables which are not compatible with each other, in the sense that we are not allowed to know precisely the value of, in this particular case, for instance, precisely know the value of the z and x components of the arrow simultaneously. By the way, we did this experiment with z and x as our examples, but if you repeat this experiment with another pair, for instance the xy pair components of the arrow or the yz components, we'll again find the same result. Now, you may have heard about the uncertainty principle in relation to the position and momentum of a particle, but it turns out that the uncertainty relation is actually very general and fundamental to all quantum states, where you are able to not simultaneously measure components of, let's say, spins of a particle along the different coordinate axes. Now, in order to really understand this and develop this idea further, we need a few more mathematical tools. So in the next parts of the video, we're going to do just that. We're going to develop a little bit more of the mathematical machinery so that we can write this uncertainty principle using mathematics, using concepts from random variables, which we've already talked about, and using concepts from non-compatible operators, and one example of which we just saw through this experiment. Thank you.